to take you through continuity of limits of functions. I'm going to take you through continuity of limits of functions. I'm going to do this example as I also explain more about the continuity of limits of functions. It's like this. F of x is equal to x squared plus 2x plus 1. They're saying that show that the function this function is continuous at x. That this function is continuous at x equaling to 2. To test for the continuity, show that this function is continuous at x is equal to 2. You know it very well that for a function to be continuous at any point, the functional value must be equal to the value of the limit. So we are going to first compute the functional value. If they tell you to compute the functional value, you bring this value and you just input. It gets input as I'm going to do for you here. You're going to find the functional value as the input x value as 2, which is equal to 2 squared plus 2 into 2 plus 1. This is going to be equal to a 4 plus, this is 4 plus 4 plus 1, which is equal to a 9. This is our functional value. So we are now going to find the limit, and we see whether the functional value is equal to the limit of this function. The limit of a function as x approaches to of this function, which is x squared plus 2x plus 1. So we are going to input this 2 into this function, which is equal to the limit of as x approaches 2, which is 2 squared plus 2x, 2 into 2 plus 1, which is equal to 9. Since the functional value and the limit are equal, the function is continuous. In case of these functions which are not rational, you just input what they have given you. Let me say they have given us x is equal to a. You just input for the function and the limit. For the functional value and the limit, I think they will all be equal. And for this case, the function will be continuous. For this case, the limit will exist because the functional value will always be equal to the limit of the function. So I'm going to also do the next example. The next example is show that this function f of x is equal to x plus 2 over x minus 1 is continuous. It's continuous at x equaling to 3, but this continuous at x is equal to 1. function to be continuous at a certain point, the functional value must be equal to the limit of that function. So we are going to first calculate for the limit of this function. The limit as x approaches 3 of this function, which is x plus 2 or over x minus 1. Is going to be equal to the limit as x approaches 3, as x approaches 3 of, then we are going to substitute our x value into where we have x in this function, which is 3 plus 2 or over 3 minus 1. This one is going to give us 5 or over 2. Then we are done with finding our limit of this function. Then we are going to calculate the functional value of this function. The functional value means you just substitute in the value of x such that we see whether this function is continuous or not. So this is the functional value. We are going to substitute in 3, which is equal to 3 plus 2 or over 3 minus 1, which is equal to a 5 or over 2. Since the functional value, so you go and conclude. Therefore, we are going to say since the functional value is equal to the limit as x approaches 3 of the function of x. Since the functional value is equal to the limit as x approaches 3 of the function of x, comma, the function is continuous at x equaling to 3. Then the question continues. Remember, we have been calculating from here, show that the function of f of x this is continuous at x is equal to 3. And now we are going on this part, but discontinuous at x is equal to 1. Discontinuous means the function is not continuous at this point. They are telling us to test whether this function is discontinuous at x is equal to 1. So we are going to input in our 1 and see whether we are going to get and see whether this function is continuous or not, which is f of 1, which is equal to 1 plus 2 or over 1 minus 1, which is equal to a 3 or over 0. I think you know very well that if we get a 0 in our denominator, this implies that this function is not continuous, since we are not getting an exact value. So you conclude like, since we just say that the function is discontinuous then after this example, I think you've understood it very well. And I'm going to do the last example. example goes like f of x. The last example is to determine the value of k such that f of x is equaling to x squared minus k squared x less or equal to 2 and kx plus 5 for x greater than 2. Determine the value of f of k such that this function comma is continuous at x is equal to x is equal to 2. From here we are going to find the value of k as we've been required to do so. You know it very well that from here we are going to compare the left hand limits and the right hand limits. So I think you've been explained how to find the left hand limits and the right hand limits. We determine the right hand limits, the left hand limits from here. You look at these symbols, the less symbol, the less than symbol and the greater than symbol. The less than symbol means this is the left hand limit, and this one, the greater than symbol, the greater than symbol means the right hand limits. From here we are going to first find the limits. We're going to compare the limits as x approaches to of f of x equaling to the limits as x approaches to the right hand limit of the function of x. Our left hand limit, I think I've already explained how to find the left hand limit and the right hand limit. Then we are going to substitute our left hand limit and the right hand limit, which is x squared minus k squared is equal to kx plus 5. Then here we are going to solve mathematically. I think all of you can solve these. Which is equal to x squared. We are going to correct like terms together. No, from here we are going to first. From here we are going to first input. Remember we are calculating the limit as x approaches to. So we are going to input our 2 to where in the places of x. This is going to be equal to 2 squared minus k squared, which is equal to 2k plus 5. This is going to be equal to a 4 minus k squared, which is equal to 2k plus 5. I think from here we are going to get an equation which are going to solve, which is you're going to take this k this side so that we make it a positive. K squared plus 2k. You're going to remain with a 0 this side. We're going to also put up this 4 this side. 5 minus 4 plus 1. Then this is our equation. We are going to solve this such that we get the value of k. K squared plus 2k plus 1 equaling to 0. Then we are going to get two numbers such that when we multiply them, we get a 1, and when you add them, we get 2, which is going to be equal to k squared plus k plus k plus 1, which is equal to 0. We factorize out the common numbers, which here, when you factorize out, we are going to factorize out k, which is common here and here. We are going to remain here with k plus 1 plus factorizing here, we are going to factorize out 1, which is going to be equal to k plus 1, which is equal to 0. K plus 1 into k plus 1. From here we are going to conclude, since we have the similar brackets, we are going to say our k is going to be equal to 1. Then you know it very well that we have to conclude. I'm sorry. Remember, I have k plus 1. It's going to be negative 1. So we are going to substitute our k back into this equation, which is equal to f of x equaling to x squared. Since our k is negative here, it's going to be plus k squared x greater or equal to 2. This one becoming a negative x. We can write this as 5 minus x, comma, x greater than 2. I think you are now content with the continuity of limits of functions. I'm so sorry. We are going to conclude. We are going to conclude our equation as x squared plus 1, I think, because 1 squared remains a 1. X less or equal to 2, and 5 minus 1. Remember, we are going to substitute our k here, which is going to be negative. This is x. Negative 1 times x plus 5. We can interchange and write it like this, which is x greater than 2. Let me think you are now content with the continuity of limits of functions. Then I can give you some other examples to try out in your free time. I'm going to just write them, and then you'll be able to solve them maybe in your free time. I think you're now content with the continuity of limits of functions. These numbers are just to try out. I'm not going to solve them. Number 1. The limit as x tends to 4 of x squared minus 4x plus 1. Number 2. The limit as x tends to 2 of 1 minus x into 2 minus x. Number 3, the limit as x tends to 0 of x squared minus 2x minus 0 out of x minus 0. Number 4, the limit of x cubed plus 3 over x squared plus 2 as x tends to infinity. This is infinity. Number 5, the limit as x tends to infinity of x cubed plus 3 over x squared plus 2. Thank you for listening.